Hello and welcome back to CS210. In this video, we will discuss about nonlinear data structures. But we will focus mainly on the combinatorial structures called graphs and trees. We will discuss different types of graphs and how we can represent it on a computer. So we will discuss two different representations, one using adjacency matrix and the other one using linked list representation. Let us start with an informal definition first. So, a graph is a mathematical structure or sometimes called a combinatorial structure for representing relationships. Consists of a set of nodes connected by edges. So, graphs have a history dating back noong 1736 pa when Leonard Euler solved the seven bridges of Königsberg problem. The problem asked whether it was possible to visit all four areas of a city connected by seven bridges, while only crossing each bridge once. The map illustrates the four main areas of Königsberg with seven bridges. Euler modeled the map to highlight only the relevant data to solve the puzzle. And then nodes in the graph are the four main areas in the map A, B, C, and D, while edges in the graph represent the bridges. So in general, graphs can be used to model relationship between different entities. For example, in social network, vertices could be a person or a specific user profile, and edges could be friendship connections or interactions like messaging or reacting to posts. In transportation, graphs can also be used. For example, in a train station, vertices could be the station, connections are the train tracks, and then in a road network, vertices could be landmarks, edges could be the roads connecting these landmarks. So beneath this powerful modeling capability, graphs are modeled mathematically. So this is covered in your discrete math, but let's have a review of some of the important definitions. The basic definition of a graph is an ordered pair. So we have V and E. V is the set of vertices or nodes, and then E is the set of edges, so sometimes called arcs. So for the rest of the course, we will use the term vertices and edges just for consistency. And here's an example in its graphical form and its corresponding mathematical definition. So here we have G, which is a pair, V and E. V is represented as a set. So the set contains A, B, C, D, E, and F. Edges are represented as a pair of vertices. So we have AB, AC, AD, BC, DE, and DF. So two vertices A, D is in the set of edges if there is an edge connecting both vertices in the graph, for example, like A, B. So we say that two vertices are adjacent if there is an edge connecting them. For example, A and B are adjacent because there is an edge F connecting vertices A and B. We can also use the term adjacent to edges. We say that two edges, E and F, are adjacent if there exists a vertex that these two edges are connected to. To say that a vertex and an edge are connected, we use the term incident. Now that we have defined the basic terms like adjacent and incident, let's define the degree of a vertex. The degree of a vertex A is the total number of edges incident to A. For instance, the degree of vertex A is equal to 3 because A is adjacent to vertices B, C, and D. Okay. A walk is a sequence of vertex and edges that hold the following three conditions. So the first condition is that a walk should have a non-zero length. Second, all the vertices and edges should be a valid vertex and edges of the graph. And then lastly, this condition, which means that every edge should be incident to the prior and subsequent vertices in the walk. So for instance, we have the simple walk of our graph with length 6. Next is a path. A path is a sequence of vertices where each vertex in the sequence is adjacent to the vertex next to it. So we often refer to a path by a natural sequence of its vertices. So for example, A, B, E, D, or A to D. The number of edges of a path is its length. So for example, path ABED has a length equal to 3 kasi we have 1, 2, 3 steps before we can go from A to D. Moreover, we use the term distance to identify the shortest path from U to V. Now we move on to cycles. A cycle is just a path but with a common first and last node. So a cycle visiting all nodes of a graph is called a Hamiltonian cycle. On the other hand, a cycle visiting all edges of a graph is called an Eulerian cycle. Now let's move on to the different types of graphs. Here we are showing an image that you're already familiar with. From this graph, we know that A is adjacent to D and D is adjacent to A. If, for example, this is a model of a road network, these edges could be a two-way street connecting places or landmarks. So one can traverse the same road to and from A and D. But some roads are more restricted than others. So in highly urbanized areas, one way to regulate traffic is by having one-way streets. So to model these restrictions, we can use a directed graph instead of an undirected graph. In a directed graph, a line segment is replaced with an arrow, but we can also represent bidirectional properties of an undirected graph by creating two opposite arrows connecting two vertices, as highlighted in these two graphs. Another way of looking at it is that directions can also add dimension of information. For example, like relationships of the same type but in opposing directions carry different semantic meanings, like expressing a dependency, or like in our road network example, it can indicate a flow. For instance, directed graphs are used to model processes, sequence of events, financial transactions, such transfer of funds, and many others. Next is the definition of connected graphs and components. A graph is called connected if any two vertices of a graph is linked by a path, or equivalently, for every pair of vertices in a graph, there's a path connecting those two. So for instance, here we are showing a connected graph. There is a path that connects every pair of vertices in this graph. If there is at least one pair of vertices that is not linked by a path, then the path is called a disconnected graph. And a disconnected graph is composed of several connected components. Here we have a disconnected graph containing three connected components. So we know from the previous topic that cycles are paths that start and end at the same node. A graph without such cycles are called an acyclic graph. And on the other hand, if a graph has at least one cycle, it's called a cyclic graph. So for instance, graph 1 and graph 2 are examples of an acyclic graph. We have directed and undirected acyclic graphs. On the contrary, we can see cycles on graphs 3 and 4. We have cycles DCAD in graph 3, while we have multiple cycles in graph 4. So to name a few, we have DCAD and CFBC. We also have a closed cycle with a repeated node C for BFC, DACB. Note that in acyclic graphs, it's impossible to start and end on the same node without retracing our steps. Directed Acyclic graphs naturally arise in problems with scheduling, genealogy, and the version histories. Okay, so let's try to define a tree using the concepts from graphs. An acyclic graph is called a forest, okay? But if all vertices of a graph is part of a single connected component, then it's called a tree. By default, we have an unrooted tree, but we also have different types of trees. Let's start with the one with the root. So it's called the rooted tree, and it's a special type of graph, so we are still dealing with vertices and edges here. Here, the vertices can have a classification, can be a root, an internal node, or a leaf. Unlike the tree that we are all familiar with, a tree in computer science has its root in the topmost part, while the leaves on the bottom part. The vertices between the root and the leaves are called the internal nodes. Edges in a tree are also called branches. So a rooted tree exhibits hierarchy. The root node is called a parent to all the internal nodes that are adjacent to it. All internal nodes adjacent to the root is its children. So you can imagine how this model is synonymous to a family tree, except we only need one to become a parent. Here are some important terms to encounter. The height of a node is the length of the longest downward path to a leaf from that node. So the height of this internal node is 2. This one, the height is 1. And the height of the root is 3, which is the height of the tree. A subtree of a tree T is a tree consisting of a node in T and all of its descendants in T. And if each node has at most 2 children, it's called a binary tree. Another special type of tree is called a spanning tree. A spanning tree is a subgraph that includes all the nodes of a larger acyclic graph, but not all of the edges. Here we can see a spanning tree of a graph. Note that we can have more than one possible spanning tree given a graph. One particular spanning tree is called a minimum spanning tree. Given an edge-weighted graph, the minimum spanning tree connects all the nodes of a graph with the least weighted path. We will discuss more about minimum spanning trees when we review greedy algorithms. As you may have noticed, trees have fewer edges compared to general graphs as shown in the previous examples. We can categorize graphs in terms of the total number of edges. Some graphs are sparse, some graphs are dense. And there are special types of graph na pinakamaraming possible edges, and we call it complete graphs. So, we have a metric called density to describe such property, and it's computed as follows. A special type of graph is called a complete graph and denoted by k sub total number of vertices. So for example, this is a k6, sometimes called a clique. And the density of complete graphs, cliques, or k sub n is always equal to 1. So if we have a sparse graph, the density is some number close to 0. Most graphs based on real networks tend towards sparseness, so mas mabababa yung density nila. This is the case where practical limitation come into play, like how many actual wires, pipes, or connections, roads, friendships you can establish at one point. Next is weighted versus unweighted graphs. Unweighted graphs have no weight values assigned to their nodes or to their edges. For weighted graphs, these values can represent a variety of measures such as cost, time, distance, capacity. Basic graph algorithms can use weights for processing as a representation for the strength or value of these relationships. Many algorithms compute metrics which can then be used as weights for follow-up processing. Some algorithms update weights values as they proceed to find cumulative totals, lowest values, or optimum. So, a classic use for weighted graphs is in pathfinding. Such algorithms compute the shortest, cheapest, or fastest routes or paths between different locations or nodes. Now, let's move on to discussing how we can represent these models in a computer. We will discuss two possible representations with their corresponding advantages and disadvantages. We will describe how certain representations are more appropriate compared with others in terms of representing different graph types. So, the most simple representation is called an adjacency matrix. In the adjacency matrix representation, the rows and columns are presented by the graph vertices, and the contents represent the edges. We can see the mapping among the vertices A to D. The contents of the matrix is either 0 or 1. So the content is 1 if there is an edge connecting two vertices. So for example, if we look at the first row, we see that we have 1 in columns B and D, while we have 0 for A and C and E. A graph having n vertices will have an adjacency matrix with dimension n by n. Since we have bidirectional edges, the resulting adjacency matrix is actually a symmetric matrix. The lower triangular is a mirror of the upper triangular. Since we do not have self-loops or an edge connecting a vertex to itself, the diagonal of the matrix is equal to 0. We can also use adjacency matrix to represent directed graphs. The corresponding adjacency matrix is no longer a symmetric matrix. So for instance, we can see that the element in A to B is 1 while B to A is 0. Likewise, the elements in the diagonal are all 0 due to non-existence of self-loops. We can incorporate edge weights in a graph by using adjacency matrices. So instead of just 1 or 0, we can include the edge weights inside the adjacency matrix. Let's move on to the second type of graph representation, and here we use linked list. Each vertex is represented by a list or a linked list, and the contents are the vertices that are adjacent to it. So for example, for vertex A, we have this corresponding linked list, and we have B and D in this linked list because B is adjacent to A and D is adjacent to A. Here's a linked list representation if we have a directed graph. Likewise, we have a list for each vertex. Each list contains vertices that are reachable via a single edge. So in a directed graph, the sum of lengths of all the adjacency lists is equal to the number of edges present in the graph. And here's the corresponding adjacency list if we have a weighted directed graph. The edge weights are also included in the linked list. So instead of having just one data and a pointer, we have two information that we can record in a node. Here are some of the advantages of using adjacency matrix. We can determine if two vertices are adjacent to each other in constant time kasi we can just directly access the content of the matrix. We can add and delete an edge in the graph in constant time because we can modify the content of the adjacency matrix. On the contrary, here are the disadvantages of using adjacency matrix. The size of the adjacency matrix is always n squared, where n is the total number of vertices. Suppose we have a graph with 1,000 vertices and isa lang yung edge niya, then we are required to use 1,000 squared for the representation of that graph. For traversals, if we have an adjacency matrix, traversing the graph requires n squared time. Whereas if we have an adjacency list, we can traverse the graph in cardinality of V plus cardinality of E using adjacency list. So this is actually ideal for sparse graph if we have an adjacency list representation. Now, you may be wondering, when is it advantageous to use adjacency matrix representation? Well, if the graph is a dense graph or it contains edges in the order of n squared, then it is better to use the adjacency matrix as compared to an adjacency list. This is because the size of both adjacency list and the adjacency matrix will be comparable if we use adjacency matrix representation. If we want to perform operations like add, delete, or check that the vertices are adjacent very frequently, just like what we are doing whenever we check reachability or path finding, then it is recommended to use adjacency matrix.